Hello, we will see length of a curve. Recall that if you have a curve R, which may look like this, then we want to measure a tiny bit of length from here to here. What do we do then? We chop it up into small pieces. If L is the whole length, then DL is this little length. And by zooming in very, very much, we can assume that DL is a straight line. From this, we can imagine like an infinitesimal x coordinate and an infinitesimal y coordinate, such that this equation holds. So the object we wish to find is this DL, so we solve by putting the square root on the other side. Then the length will be the integral of all of those little DLs across this interval from A to B, and by solving for DL, we have this expression. As I said in class, this expression with dx and dy makes no sense in the usual sense of calculus, but we have to remember that our curve looks like x of t and y of t. So this dx represents the derivative of x, where x is this guy, the first coordinate of our curve, and dy is the derivative of the second coordinate. So by replacing this in this equation, we have x prime and y prime squared, and those are terms that are functions in terms of t. So we can solve that in a t integral to obtain the length. Let us consider the example of the curve r of t equals sine t squared and e to the t. So the x coordinate is sine t squared and the y is e to the t. The parameter has bounds 0 to pi halves, so those will be the bounds that we have on the length integral. The parameter bounds are the bounds of the integral, and we're also asked for the endpoints of the curve besides the length. So let's find the endpoints really quickly. We have seen in the previous example that we just have to evaluate r at the bounds of the parameter. So we plug in 0, we plug in pi halves, and see what we get. We have that r of 0 is the first endpoint. We have sine of 0 e to the 0, and this is 0, and this is 1. Okay? Sine 0 is always 0, and e to the 0 is always 1. On the other hand, for pi halves, we have whatever these expressions may be, they are real numbers. That's the important part. Now, let us see how to find the length. What we will do is that we will differentiate our curve. Differentiating the curve means that if we have r of t equals x prime and y, x and y, we can differentiate r, and what it means is that we differentiate both entries of our curve. And these entries are precisely what we are looking for in the expression for the length of our curve. We have an x prime and a y prime. So it suffices to differentiate this. And as I was saying, differentiating an array is the same as differentiating entry by entry. So the differential of our curve means taking the derivative of both entries. So the derivative of sine t squared by chain rule is the derivative of sine evaluated at t squared times the derivative of the argument, which is 2t. This we will take to be our x prime, while the derivative of e to the t is just e to the t again, and this is our y prime. Now, we will plug them into the formula because we now have the x prime and the y prime we were looking for, and now we have that the length of the curve is the integral from 0 to pi halves. Remember, these bounds are the bounds of the parameter of the square root of x prime squared, here you have the square, and y prime squared. Okay? This whole expression is the DL, the little line element of this curve. The line element will come in handy because it is what it is used in all of the other problems which have to do with mass, with rotations, and all of the length problems, you have to find the DL. So it's very important that you remember how to find it via the Pythagorean theorem. Really quickly, let me show you an image of how this curve looks. We are now on the plane, and we will see the curve, which was r. It was sine t squared e to the t from 0 to pi halves. This is the curve. As you can see, it's a curve which comes from here to here, and that's the whole curve, like in the interval for the parameter. The endpoints are evaluated at 0. This is 0, 1. You can see that point over here. And the other point was sine of pi squared over 4th, which is what you get when you evaluate pi halves, and e to the pi halves. And that point is this point over here. We're actually not concerned about the decimal values. Those are there just because they are an approximation. And so these are the endpoints. And the length is the distance from here to here. But as you can see, it's this curve, okay? I remember that in the definition that I had shown you, the curve looked bigger. That is because the bounds of the bigger curve were bigger than the actual bounds that we were looking for in the length. This curve is actually much bigger than this. We can see a bit bigger curve like this. This curve is the same curve, but with the parameter going from minus pi to pi. And this means that we can extend it. So it just goes like here. It has a wave, and it continues up there. But basically, the portion that we're interested in is the curve which goes from here, from A to B. And that is when we just take the parameter which goes from 0 to pi halves.